Great. So we talk about algorithmic game theory. We discuss some of the important aspect of it. We talk about briefly that in game theory, we talk about the social behavior and social interaction of different people or different, essentially, creatures. It can be animals, it can be robots in the future. And then in the algorithmic game theory, we try to have some mechanisms, or sometimes they call it mechanism design, that on top of the, just make sure. So we just want to make sure that the objectives of these individual people are also considered. So we'll try to design some mechanism. In some sense, it is a multi-objective function that we try to optimize. Objective of the mechanism designer that we discussed, for example, if we have an airline and then the people want to board, then you may define what would be the objective function here. Maybe one objective function would be the comfort of the people. But this comfort would be multiplied or weighted by like how important is that person. And of course, you don't want to make some certain people not important at all, because if not too many people, yes, maybe if you have airline and some people have status with you, gold, platinum or higher, you want to make them happy, so you have a higher weight for them. But always there is a trade-off. You need to care about the other people, because if the other people are not there, then probably not these people also, they may discontinue with you, and you don't want to send an empty flight. So you need to have some kind of trade-off. What are the exact objective, like the weights for each of them? What is the exact objective function? These are something that actually you need to have a deep dive on it and understand it and try to put it there. So that's for objective. Now, maybe for individual guys, it's a bit easier. Maybe you can say the level of comfort of each people. Maybe that you can define. Maybe here comfort, again, is a function of time to get to your seat when you are essentially waiting in the airline to get for a flight to essentially to board, or maybe some other things. But maybe you can define for each of these. And then overall, you try to design some mechanism that everyone is good. So that's essentially the concept of algorithmic game theory or mechanism design that we discussed. And we talk about the concept of equilibrium, which is essentially is a point in which no person or no agent in the game wants any charges. Everyone is happy with the thing that they currently there. And in some sense, this is a state that everyone is happy to some level, or they cannot get anything better by changing their, for example, their current strategy in a different way by some definition of it. So I think this is a good definition, is that like an equilibrium is simply a state of the world where economic forces are balanced, and in absence of external influence, the equilibrium values of economic variables will not change. We talk about some two important concepts of equilibrium. So when you have a game, all of them come naturally. When you have a game, there are some kind of like mechanism design and some other people. And again, these people, you may have even like maybe in some sense, mechanism designer is not maybe that much different from this set of people. Or you may have some hierarchy of game people that are doing. Maybe there are some maybe smaller or less powerful agents, then more powerful, and then the mechanism designer for everything. If you think about this one, for example, the whole government, if you think about the government, yes, there are individual people, then there are companies that they have, some of them like big tech, they have lots of influence, and then there's the government that is doing that. And like, you know, the big tech even may change the government strategy. So that is a whole complex things. And in this case, then you want to find some kind of equilibrium. It means that like everyone is somehow happy at some point. If no one is no external thing, if there is no war, for example, then everyone somehow is happy. But if there is a war, then, for example, government generally becomes more powerful. It may ask, for example, big tech or some other companies to generate something for the war. This is one of the things that actually is in the US law, that US government, like they use that one in COVID, for example, that they more pressure on that. So if there are some external thing from external, I don't know, planet or external creature like COVID, etc., then the situation may change. That's one. So this concept of equilibrium is the one that everyone is happy current state, nothing is happening. And as we discussed, there are two important concepts that we will talk about. It one is the Nash equilibrium type of things that we will talk here, and also the concept of market equilibrium. And then there are this concept of fairness, for example. So these are some of the work that, I mean, work like Danny has a paper on it, or like other things. That's another thing. But what's the meaning of fairness? What are the good things about fairness? And that's another things that will be discussed in this course as well. And as well as auction design, etc., and the new concept that we are talking about it. So let me see, is there anything here? And we want to do it. So I think good. So we are talking also even for equilibrium, there are different concepts that we talk about. For example, price of anarchy, price of stability. And we discussed that, I mean, like the concept of existence of equilibrium is something that the people in economics, they have considered, but somehow computing an equilibrium state is something that we are talking more in computer science, or the time that a state essentially reaches an equilibrium is something that we talk in computer science. Good. Now, given that, let's go and define a little bit formally the things that we are talking about it. Give this. Good. So, as I mentioned, I mean, there are lectures for introduction to computational game theory. These are more basics, essentially. That is already available in my YouTube Hajiaghayi. If you go to the channel, and there's a playlist for that. And it is required, I mean, that you are watching them and you know about this, because we are building on top of that, and we go further from that. But some of the things that some of this actually, it is mentioned here. It is formally about this analyzing normal form games. Generally, when we consider an n-person normal form game, we have a set of people 1 to n of agents or players, and each agent I has a finite state AI of the actions that he or she can take it. Good. So these AIs, you can think also, we will call this AI pure strategy, that I will take this action, or these actions. So, and an action profile, we often talk about an action profile. It is a vector, essentially, of actions that each person can take. So this is A1, A2, AN, and these are the action profile. And the set of all possible action profiles essentially would be the multiplications of this. If you, this is, then for this, each agent I, we define the UI, the action, the utility of agent I, considering the fact that the first agent takes action A1, the second person takes action A2, and the last person takes action AN. What would be the utility of this person? And you can think about, we are giving some examples of these games. So this is a typical thing, for example, that we are discussing here. Generally, if we consider this kind of actions, we can consider the whole thing in a matrix. That in this matrix, we have the like the different each agent, like this is player 1, for example, we call it also row player. So this is the player 1 and this is player 2. This is called column players. This is the simplest case that there are 2 agents, but even 2 agents actually is quite interesting. Then you have agent 1 and agent 2. Then in this case, each of these people may take some actions. And then this is the utility that they will get it in this case. So if, and again, an action profile would be each cell of this big matrix. So the action, so here essentially means this guy takes action 3, this guy action 3, and then this is the first guy gets as a utility, and this is the second one that gets as a utility. Good. This is the other one that if this guy is take 3 and the other one is taking 1, then this would be the type of essentially utility at each of them. So far, everything is deterministic. It means that these people are taking this, the actions, and they get this money essentially or utility. Good. No, one famous game essentially here is this one. This is the prisoner's dilemma. We talk about it because I want to add more to it. Maybe use this one for this. What is the idea? So this is the scenario, this is a typical thing, but it is more interesting than this. So there are police is holding 2 prisoners as suspect of committing one crime. For each of them, the police has enough evidence for 1 year prison sentence. But they want to get enough evidence to get essentially 4 year prison sentence. Now, this is the strategy. This is, in some sense, this is the mechanism designer is doing that. They tell each prisoner, if you testify against the other prisoners, we'll reduce your prison sentence by 1 year. Good. Now, that is the idea. So this is the mechanism. And then what are this? This is like the, between these prisoners, they have 2 options, C and D. C means that they are cooperating with the police. And D means that they essentially, cooperate actually means you are cooperating with the other prisoners and you refuse to testify against. And defect means that you testify against the other prisoner. What is the incentive? Because you know that if the other person is not doing the same thing for you, then you get some benefit out of it. Because then your 1 year would be essentially you get some kind of 1 year like 1 year is the prison time, but because they will reduce their time in prison for 1 year, then essentially you don't get any time in jail, which is very good. So these are the, so in that case, for example, we can just have this matrix. This is the normal form matrix. So they can have each of these prisoners, they have, this is like symmetric in that sense. They have CD and CD here, and each of these people may decide to, if both of them cooperate, they get essentially 1 year essentially in prison. If one of them cooperates, the other one does not cooperate, the person who essentially cooperated in that sense, that person gets -4. But the person who defected and mentioned the other one, they get 0 because they have 1 - 1. This is essentially symmetric, the same thing here. And the other case is that both of them defect, both of them then say something against each other. In that case, both of them, they get 4 years in prison, but because they defected and somehow cooperated with the police, then they get 1 year less. So it would be -3 or 3. And again, these minuses, you may also remove them, essentially the number of years in prison. So this is like the things that we are showing. And this is the utility that we are talking about. So that is one game. And we will come back to this because I want to say some important things about these games. Let me just give another example here. Okay. Good. So let's go back to this definition that we had. So that was the prisoner dilemma. I will come back to that, but there are some other things that I want to go more than that. Okay. So this is a prisoner dilemma. Essentially, with just some numbers, you can always do this kind of affine transformation. You may add something to the, like the number of years. We had it minus, you can add essentially 5 to each of them. That is essentially fine. It keeps the utility the same. By the way, lots of this discussion, I'm doing it essentially, again, in the undergrad game theory. Please go and watch those because there are more details out there. I don't want to go through that. I want to cover more essentially here. But I need to just something that I can build up on top of that, such that you remember that. And this is like the same thing that we had. This is the confess versus essentially confess means you essentially defect, and silent means that you'll cooperate with another person. But these are the things that you will get. So then I defined also the action profile. So what was the action profile? Action profile essentially was this kind of that each of these agents take one action. And if each of them takes actions, then you are essentially falling into one cell of this matrix, because this is essentially like, you can consider this is two-dimensional because there are two players, but it can be more than that. It can be three-dimensional if there are 3 players, and so on and so forth. So in that case, then you will consider each action profile will put you in one cell of this matrix. So that's the way essentially the data structure that we can represent this matrix. And then the utility for this guy would be the utility that it gets it. So for each of these guys, if there are 2 players here, we have 2 utilities that we will get it. If this is the action profile, is this. Action, also it is called pure strategies. So action profile and pure strategies are the same. However, so we have this concept. So this was the thing that we discussed about actions. Now, what about strategies? And by the way, so one thing which is important, for example, we will use these notations generally, that when we say essentially, this is AI. Yeah, so this is, we are just using AI to say essentially this is the action that agent I has done it. And we are using A minus I, means that in this vector that we have, just drop AI and everything else. That essentially means AI bars. The same way we define SI and SI bar. So if we consider strategies to be pure, no randomization, that means that here SI and AI would be very similar, would be the same type of thing. You will take some pure strategy, and then you have a vector, essentially this vector S of these guys, S1, S2, Sn. This is essentially would be the same as action. The thing that it becomes different, it makes it different, is that this might be not pure strategies. My action would be some distributions over all possible. My strategy might be some distribution over all actions that I have, or all pure strategies that I have. So actions and pure strategies are. In this case, it is called mixed strategy. So in that case, SI would be more complicated. So you will say that essentially for each of these actions that you have, A1 to AK, and say these are the actions of player I, because it might be different for this. For each of them, you have a probability distribution. What's the meaning of probability distribution? It means that essentially each of them, you take each of them with some probability, and some of this probability would be equal to 1. That's the meaning of a probability distribution. So in that case, when we talk about SI and SI bar, then, I mean, each of these guys is more complicated. It's not just a pure strategy, it's a distribution. Essentially, it's a vector itself that says that for each of these actions, what are the probabilities that I make? Good. That's the one essentially that we are considering here. This would be the, we will call this one mixed strategies. So this is, that was pure. And this one, which is essentially, this is the probability distribution. This is essentially a mixed strategy. Good. Yeah.
So what's the behavior strategy or mixed strategy?
No, behavioral strategies, then when we have essentially some kind of representation of essentially the graph in the other form. This is not normal form game. There are other things. We will talk about it. But generally, I mean, there are in lots of cases, behavioral strategies and mixed strategies are somehow similar, but not all the time. If you go to my lectures, essentially, again, for introduction to game theory, we talk about these behavioral essentially strategies. When we talk about the other forms, not normal form games, essentially. And we discuss exactly the example that, for example, a behavioral strategies, generally when you are considering them essentially as a tree of actions, then you can define behavioral strategies. And behavioral strategies, in short, it might be the case that causes some kind of independence between the strategies of these guys. You have some probability, but you have some maybe joint probability. And they are not completely, there is some essentially more like dependence are going there. But there are lots of times they are similar, but not all. And again, that is the case there. You can just go on. We may cover later in this course as well, but that's a part that you can just go and read them essentially. So this is like, I think if we want to, this is the, this is the perfect information extensive form games. If you go there here and see the slides and the lectures, this is for the undergrad lecture, but you can also see it in the the videos. There we talk about it and then we define the behavioral strategies, etc. This concept of subgame, perfect equilibrium, etc. But that's the thing that we will talk. You can see more there. Great. Let me go back to this one and delete everything. Okay. Now, let me introduce these two other games which are important here. The other game, which is, there are essentially three important games that I want to mention because I want to discuss this one and then go from there. One is the Battle of Sexes. That's the other game. So here, essentially, again, these are like a famous game, Prisoner's Dilemma, Battle of Sexes. This is the one that it is called more coordination game. What's the meaning of that? In this game, there are, two players, a boy and a girl, who decide on how do they want to spend the evening. If they both consider essentially two possibilities, going to the basketball game or going to a softball game. Again, one, you can consider husband and wife, they are going to, for example, opera concert or versus going to football. And the boy prefers baseball, whereas the girl prefers softball, but they would prefer to spend the evening together. So in that case, this is like the thing. This is again, the boy and each of them baseball, softball, and then this is the utility that each of them gets, essentially the same. And again, this one, the other version that we are doing, for example, on the other course, this is like husband and wife. They want to decide to go with opera or like a football game, and then, but they prefer still to be with each other. So, for example, here it said that if they essentially the girls and boys, if they want to go to baseball, the boy will be more happier, the girl will be less happier. If, however, if if the boy goes to softball and the girl essentially go to baseball, then each of them will be quite unhappy. Each of them get essentially one in this case. Maybe if they go essentially, boy goes to baseball and the girl goes to softball, then each of them get two because they are not together. This is the thing that they are not coordinated. But as long as they are going together, maybe if they go both go to softball, then the girl will be a bit happier versus the boy. So that's a typical thing that is called coordination game. It is important. And the other one which is important, essentially the matching pennies game. This is the third game, which is super important. In the matches, I mean, essentially you have a penny and you choose from two strategies, heads and tail. So that is essentially you are tossing a coin there. And the player wins if the two pennies match and the column, the other player. So here, this is like, we can, sometimes also we call this one as a row player. This guy wins if they are essentially doing, if the first player is essentially the match, and otherwise the other person wins if this is not a match. Good. And for example, if there are both head, in this case, we call also this one row player. Sometimes we call this one column player. So if in that case, the row wants the match. So if they're both head, he gets one. If and in this case, the other person gets minus. If it is tail, this guy gets, if this is head and this is the tail, then this guy gets -1 and the other one gets 1. This is the utility that they will get out of this. The same thing here also, again, if head and tail, this guy gets -1, the other one gets 1, and vice versa. So, and note that so far, for simplification, we consider that these are one-shot games, that in one shot they are playing, and then they get the utility out of it, as I have described here, like 1 - 1, etc. And good. This is the third game, which is the matching pair. Now, let's go there. I want to talk about two concepts of essentially equilibrium here. In particular, like what are the Nash equilibrium, and how can we get the results essentially? How can we even compute? Good. So the first thing, so there are several concepts of equilibrium. One of them, as I mentioned, the most natural one, or like natural in a sense that it happens more, is a Nash equilibrium. That Nash actually got the Nobel of Economics because of that. And the other one is market equilibrium that later we talk about the pricing in a market. Both of them are like very fundamental. Good. First, let's start with dominant strategy solution, or dominant equilibrium, essentially. So we say that a game has a dominant strategy solution if each player in the game has the best strategy, independent of the strategies of all others. Good. So that's essentially, this is a very good thing. So what is that? So we have a strategy vector SI. This is, we call it this. Sometimes we call it vector of essentially strategies, or we call it a strategy profile. Profile means vector of strategy. And these strategies can be mixed or can be they can be mixed or they can be pure. It is a dominant strategy if for each player I and each alternative strategy vector S prime. So essentially, if you consider each player I, and S is essentially the so S, like here we said that has a dominant solution if each player has this. So all of them together, not just one. All of them, they together should have this one. That if they are playing this SI, independent of what is the other thing that the people are doing, this is the best essentially. So it means that SI versus everything else, because S prime was anything else. And S minus I means everything that the other people are doing that. So if they are doing that, that would be larger than the case that this guy is doing any other strategy S prime I, and the others, they are doing S prime. So essentially, it means that if SI do anything other than that S prime I, independent of what other the people are doing, that is essentially still the best utility that we get. Good. So that is essentially, that is the concept of dominance. This is a good concept essentially, but the issue is that it's just too good to be true. By the way, we talk again more about this kind of dominant strategy profile in this introduction to game theory course. Please watch the videos there. Then you will see more examples, like where, for example, where this kind of thing will be pure or not pure. Lots of the time, if there is this kind of mix, then sometimes you can say that always there's a pure, etc. There are this discussion. I don't want to go there. I'm going to cover more than that. So that's the thing that I want to just give briefly, so that we can go above those things. Okay, so this is the concept of these dominant strategies. The other concept that we have it is this I mentioned these games. This is the concept of Nash equilibrium. This is a more realistic thing. Because as I mentioned, essentially it is just too good to be true for dominant strategy solution. We have a dominant equilibrium. Like you want to say that independent of anything that the other they are doing, this is my best strategy. This, like in real world does not happen that much. The concept which is more natural here, we say this is the Nash equilibrium. A strategy vector S is said to be a Nash equilibrium if for all players I and each alternate strategy S prime I. We have this property that if essentially UI of Si and S minus I is greater than or equal to S prime, but the rest of the guys, they are playing S minus I. So what is the difference between this one and that one? The main difference essentially is this part, that here in this in Nash equilibrium, we are talking about this Si should be the same here, but in the dominant strategy, we were talking about S prime I. So here, in some sense, we are fixing that the current strategy. We say that each of these guys, they may take some strategy. It can be pure or it can be mixed. But mixed means essentially a distribution over the strategies or actions. But in both of these cases, we are so here in the Nash equilibrium, essentially said that if everyone else does not want to change their strategy, I will stick with my strategy. This is the exact notation. It says that if I am a state, so current state strategy profile or strategy vector is S, that is in the equilibrium. I am saying that if others they don't change, means that everyone stick with S minus I in both cases. If I take any other strategy, S prime I, this can be pure or it can be pure or like mixed. Then still, then in that case, I don't get anything better. I mean, I may not, I may get the same, essentially, utility, but nothing better. Good. And this is the concept of Nash equilibrium, we consider. So one thing it is important, one term here is essentially best response. What is the best response? Here, essentially, it means that if everyone takes, if you consider S minus I, if everyone takes essentially S minus I, take the, if everyone get their, essentially stick with their strategy, what would be my best response? What would be the action that maximize my utility? Good. One thing that I wanted to mention, when we have this kind of mixed strategies, how do you compute? So if there are for example, in this prisoner's dilemma, so this is the C and D, and this is C and D. So in that case, when we have C and D, then if this guy is getting C, this guy is getting C, then, for example, this guy gets 4 and this guy gets 4. This is the utility. That's easy. That's in a pure case. In the mixed case, how we need to compute it, it would be essentially some probability. You see that this one C I will get is this probability 1/3, this is 2/3. This guy is taking this one with probability 1/2 and this one with probability 1/2. Now, if you want to say what would be the utility of the first agent, that's the way that you need to compute it. You need to say that what is the landing probability on each of these cells. So for example, here the landing probability would be, and these are independent, it would be 1/3 times 1/2, which would be essentially 1/6. In that case, what would be my utility would be 4. So it would be 1/6 times 4. So it would be 1/6 times 4, for example. Then you go to the next one. Here, what would be the landing probability would be 2/3 times 1/3, which would be essentially 1/3. And I don't know, in this case, maybe the utility was 2 times 2. And so on and so forth. You need to compute the landing probability for each of these cells and then sum it up. That would be the expected utility. So that's the thing that we talk about, the expected utility, when we have the mixed strategy. Good. So that's essentially the one for the. Now, here when we talk about the utility, if it is the pure strategy, means pure strategy utility, means essentially just one cell of these things. If it is the mixed strategy, it would be this expected utility. So when we talk about utility, it means this. Now, let's see some examples from these games. So this is like expected utility, but we may just write it as a utility. One important thing about the best response. Best response, it means that if everyone else essentially gets S minus I, what would be the strategy S that maximize the utility of? So essentially, this is the strategy S that maximize this. Essentially, the S strategy, or SI, I will say, that maximize this utility. That would be essentially the best response. One important thing is that the best response is always pure. Good. So this is a very important concept that we are feeling it a lot. Best response will be always pure. I mean, of course, there might be some mixed strategy which has the same utility, but always there is a pure strategy which is best response and gets essentially the maximum utility. Why do we have this property? Yeah.
Because if you fix others, it becomes a single player problem.
And not really. I mean, it might be the case that others are also playing mixed strategies.
Yeah, but if you fix them, fix the others.
Yeah.
Then only you can deviate.
Yeah.
You can treat this as a single player problem. It's not a game.
Yeah, that might be one view. The other way is that, I mean, yeah, go ahead.
Like if you play a mixed strategy, your utility is like an expected value of source, and that's bounded above by picking the highest paying.
Yeah, this comes essentially from this concept. We are using this one a lot for Nash equilibrium. This is a super important thing. So in some sense, when you do mixed strategy, it is like, this is a good example that I will mention for GPA. GPA is the average of your grades, correct? Like, for example, if your GPA, I don't know, is 3.3, then it cannot be the case that all your courses, the grade that you got, it was less than 3.3. Or it cannot be the case that all of them are above 3.3. Good. It means that there should be at least one that is below the, at most below, less than or equal to average, and one which is at least greater than or above the average. So the intuition of it, you can write the math essentially, but in some sense, when we take the expectation, we are doing this essentially because of linearity of expectation. We are taking each of my actions that I'm taking it, and the sum it up. So if this is the total utility that I will get, which is average because this is a probability distribution, if I get this average, at least there should be one of these, which is at least, this is the same essentially GPA thing, at least one of the pure strategies that I'm taking in my support set. Support are those that are non-zero. So support of my strategy that I'm taking for a mixed strategy are those actions that the probability is greater than zero. If it is zero, I cannot say it. But if this is greater than zero, it is weighted average. The same thing for essentially for GPA. So this thing that I mentioned, for any weighted average, it works, which is essentially meaning of expectation. At least one of these actions that I took it should be, the utility should be greater than or equal to the average. And that's exactly the reason that always there is heuristic. Good. Note that, as we discussed, that doesn't mean pure, essentially a Nash equilibrium always like exists, or this that it's a pure strategy. Everything is pure. It says that if the others can be mixed, but I have one that is pure. But the issue is that, I mean, in the one that you have the pure, if you take this pure, maybe the others want to change it. So you are not in a Nash equilibrium, but that doesn't mean that anything. But that is a super important thing. Now, let's go back and discuss these things. I wanted to. Good. So let's see, I mean, some of these three important games that I mentioned, the prisoner's dilemma and battle of sexes and matching pens. What is the situation that happens here? So here, do we have, okay, when we say pure Nash equilibrium, is the one that has what? All strategies pure. That's a good one. Why? Because we can see whether it exists or not. The only thing that we need to do is essentially go through all this we can just go through all cells of this matrix. And for each of them, check whether this strategy profile or this action profile, which is, as I mentioned, each cell is corresponding to action profile, or essentially a set of actions. So if you go to this cell, means confess, whether this is a Nash equilibrium or not, that is easy to check. So here you want to say that if these guys, and we know that this is a game, if it is a Nash equilibrium, best response is always pure. So what's the meaning of that? So in that case, if this guy, this is the confess, we can say that if this guy is essentially assuming it's confess, if the other guy changes his strategy, so this other guy, if it goes from confess to silent, then the value that he will get here would be 5. And again, depending whether we want to maximize or minimize. Say here we want to minimize. We want to say minimize. That is fine. So in that case, if this guy goes from confess to silent, then it becomes from 4 to 5. So this one does not get any benefit. And the only other action that it can take is this going silent. What about this guy? So this guy, now you're fixing this guy. This guy is confess. Now what about this guy? If this guy is going essentially from confess to silent, he gets also 5. So it means that this is a Nash equilibrium. Confess is essentially equilibrium. If the minimization is the main thing, if it's the maximization, will go to the other. Now, if you consider, now what about this one? Is this a thing? So if this guy is silent and this guy is confess, then this guy, if it changes from silent to confess, then he gets essentially 4. And we wanted to minimize, correct? So this is a not Nash equilibrium, because this is the best response is to take confess. Similarly for this one, you can say that. And what about this guy? If this guy, if this is 2 and 2, if this guy is silent, if it goes from silent to confess, then he or she gets essentially 5. So it is not good for this. But if it goes from 2, if this guy goes from silent to confess, instead of 2, it gets 1, which is less. So it means that we wanted to minimize. So this means that this is not a Nash equilibrium. If you want to maximize, it would be the reverse. It would be just this guy would be. So in that case, you can say that, for example, here, if you want to minimize, this would be the only Nash, pure Nash. What about, so this game has only one pure Nash. What about this battle of sexes? You can do the same thing, essentially. So here you try to maximize the satisfaction. So here in this one, if both they go to the baseball, they get 5 and 6. So now if it is baseball, if the other person changed from baseball to softball, it gets 1. And if this one is fixing essentially this guy to baseball, if this girl goes from baseball to softball, then it gets 2 essentially less. So this is a Nash equilibrium. No one wants to change it. What about, you can similarly, you can say this is also a Nash equilibrium. What about this case? If we have both baseball and softball, so in that case, if this person is soft and this guy, this girl goes from baseball to softball, then instead of 1, it gets 6. So this is not a Nash equilibrium, and this is not a Nash equilibrium. This is the example that shows that we can have more than one Nash equilibrium, like here 2 essentially. Good. So and then let's go to the other game that I want to say here. The matching pennies. So in the matching pennies case, now here, see what will happen. Here, if it is HH, I mean, we don't need to see the description of the game. As long as these utilities are given to us, we can talk about this naturally. So if they are in HH, so if it is HH, so this guy is 1, this other guy is minus. Good. What will happen in this case? So if this guy is H, and this guy, so this guy is keeping the H, but this guy is changing from, if like this guy, if the action is essentially becomes T, then in this case from H to T, then this, instead of 1, it gets minus. So it's not beneficial. But what about this one? If this is H and this guy is go from like this action goes from H to T, this becomes, instead of -1, it becomes 1. Good. So it is beneficial. So this is not a Nash equilibrium. So similarly, you can say this is the same here and also the same here. So you can see actually, if you check it, none of them would be a Nash equilibrium. Each of them, there is one that is going there. This is an example. As I mentioned, these are these very classic examples. One is that there is one Nash equilibrium exists. The other one in Battle of Sexes, a Prisoner's Dilemma had one Nash. Matching pennies had like two, more than one, pure. And this is the one that does not have any pure. Good. So let me delete all of this. However, this is the essentially the important theorem that Nash proved, and essentially this is the one that he got the Nobel Prize because of that. He said that any game with finite set of players and finite set of strategies has a Nash equilibrium, which is of mixed strategies. So we cannot say about pure strategies, but we can say there exists one that is mixed. Yeah.
Sorry, can you redefine pure and mixed?
So pure means essentially no probabilities. You are just take one. It's essentially action. You take any of the actions deterministically. Mixed means that you have a probability distribution for it. Good. So that's essentially the Nash. You can actually read the theorem, but I want to talk before that. Talk how can we find this Nash equilibrium? Good. This is the computational. For pure strategies, so let's simplify for now the case that we have only two players, because actually this is interesting even for this case. Let me bring this one. You can, I mean, essentially get more out of this. Let me bring this one, find the Nash. So please, as I mentioned, see the lecture for this one, especially. So we talk also about linear programming. That is also, these are like basic probability theory. Please watch these videos in particular. We talk about the basic that we talk about it. So that is a good recap. I mean, you can, of course, have much more ideas on that. But the videos for this, which is in the, again, go to my YouTube channel, Hajiaghayi, Introduction to Game Theory. There are these that you can just, so these tools that we are using, probability theory and linear programming, are essential for game theory. So, and I discuss it, I don't want to go through this one. You will watch, and please watch it as soon as possible, because it's important. Normal form game, I have defined it, I mentioned it, but there are more details there. And this important normal form games, I mentioned some of them, but you can read more about this in this important normal form game. And about the analyzing them, I will talk about the dominant strategies and other things. But this one that I want to focus a little bit more about is finding Nash equilibrium. How can we find Nash equilibrium? Good. As I mentioned, if you want to talk about pure strategy, Nash equilibrium, that's easy. What we do, and here, say for simplicity, we are considering, and this is actually interesting, even it's in this case, we are talking about two players. So here we have two players. We can represent them like this kind of two-dimensional thing. If there are three players, then it would be three-dimensional. So then we are doing that. These are the actions that this guy is taking. This is the row player, and this is the column player. The question is that, can we find a Nash equilibrium in polynomial? Can we compute it? And again, this is the question is that maybe economists, I mean, at the beginning, they said, I mean, why we should care about it? Maybe if it goes there. So they try to analyze more a structure of Nash equilibrium, if it reaches there. But here in computer science, okay, how can we find it? Because there are some benefits for that. Maybe if you know that, you can say this is the one that you can recommend to the people. And other aspect essentially is that like you want to do that, maybe you can to find the structure, you can find all of them and then discuss about the structures, etc. Anyhow, so independent of motivation, so that is the one that the people in computer science, they worked a lot on that one. And even for these two players, we say each of them have, if there are a number of them is constant, then the problem is easy. But say each of them have n actions, essentially. This n actions, this is n actions. So each of them, they have n actions. How can we find essentially a Nash theorem in the mixed sense? If you want to get it as a pure, that is easy. You will go to each of these ones and then you will. But what about if they are not pure and you want to find the mix? So the main idea here is, again, this thing that I mentioned, that always there is a best response which is pure. That is essentially the main idea that you can use it to get it. The time would be, okay. So let's consider this game, essentially battle of sexes, and see how can we find the equilibrium here, Nash equilibrium, mixed Nash here. Then you will get the idea as well. So you want to, again, so what do you do? This is like, this is a simple one. You are putting the P, this is the probability P here for husband, I will say, and yeah, assume that here, this is the husband and wife case. Husband, the strategy is that it gets P opera and 1 minus P football. But what for wife would be Q here and 1 minus Q here. Good. Now, what will happen here? Then you can write. So what is the expected utility of this guy would be essentially P times Q, because what is the landing probability of this one is PQ here. And what would be the utility in this case would be 2. The same thing, you can essentially, you can compute the expected utility for it. However, I want to write it in a bit different. I want to say that what is the expected utility of wife's action? Just consider this. So if she do opera, then she get 2 times P, correct? Because this is the probability of husband P. And 0 and 1 minus P times 0, which would be essentially 2P. What about for other case? If doing essentially football. So in that case, it would be, what is the probability that in the football case, it would be 1 minus Q times 0. Sorry, it would be P times 0 in this case. And 1 minus P times 1 here. Good. These are the formulas that I have mentioned. This is essentially the whole idea for finding this Nash equilibrium. And here, so what is the idea? Is that these 2 actions that this person gets it, if both of them is in the what was this term for it? Okay, if you consider there's this non-zero set of non-zero probabilities, what was the name for it? What is that? Support. If we consider the support of these things, that is important. If you consider support, because we are using this support, if you do consider the actions in the support, all of them, they should have the same expected utility, essentially. If you take each of them pure. Why? Because if one of them has a little bit more, then move slightly the probability distribution from this guy to other guy that has a bit more. All of them should have the same, but all of them, they should have the same utility. So what's the meaning of that here? It means that in this case, So there are two actions here. It means that 2p should be equal to 1 times 1 minus p. And then from you get p is equal to 1 over 3. Good. So you can fix the other, as essentially mentioned. I mean, like in some sense, if all others are, that if there are even more than 2 players, you can say that they are taking these actions. But I take the actions for each of these actions that I'm taking, the different things that I'm taking it, depending on the other guys. Say here, essentially, say even 2 players for now. I will get some kind of linear equation. And then I need to put all of them equal. So if there are more than 2 actions, all of them, they should have the same equation. So you can say the first one is equal to 2, the second one is equal to the third one, and so on and so forth. You will write this guy. So this is essentially one way to obtain it. So how can we get it? This one say, especially for this kind of 2-player games, which is already as general as possible as I mentioned it. You can just do this one. You write this equation. So first, you need to guess the support of each guy. How many support exists for each of this person? Like if there are n actions. 2 to the n, correct? Because all these actions that they are taking, any subset of them can be the support. So in some sense, this is the part this is the reason that this algorithm is exponential. So here, if there are n actions, this guy, it has it. So if there are n actions, this guy has it. This is 2 to the n. What about this guy? For this guy is also 2 to the n. The n is the maximum. That you need to guess what are the essentially what are these support. You will guess for each of them. Guess means try all possibility, which is, I don't know, 2 to the n plus 1, or 2 to the 2n actually in this case. Good. So you will guess that. Now for each of them, when you have that, then you can easily write this kind of linear equation, system of linear equations. You will write it for each of these players. Then you will solve these equations. All of them are linear equations. This part is polynomial, it's easy. Then you will find some numbers. However, still, it might be the case that you need to check that the whole thing that now you will solve PQ everything. You will get it. Still, you need to check that each Nash equilibrium should have this property. But doesn't mean that if they have this property is also Nash equilibrium. You need to check that any other actions that if they take it at this time. So you need to say that any pure strategies. So you will compute this one. You have P and Q, and you have this is the suggested Nash equilibrium. However, still you need to check essentially whether this is a Nash equilibrium or not. That is easy. Why it is a Nash equilibrium? If for each actions, the best pure strategy that I'm doing is getting at most the same amount that I'm getting with this mix. But checking that something is a Nash equilibrium is easy because of this thing that I mentioned. You will, for each action, you don't need to go over mix, because if you go to mix, then it is hard. But you just go through pure and see whether if I take any pure, everyone else is the same, whether I get at most the same expected utility that I will get it now or not. If it is the case, this is a Nash equilibrium. So how can you do that? You will consider all possibilities of this kind of support. This is exponential. Then you will solve the equation that is polynomial, and then you will check its Nash equilibrium. This is polynomial. So that's essentially the way that you can compute Nash equilibrium. I mean, for 2-player game. But the question that maybe 2-player games are too specific or not, this actually shown that it is not the case. So this actually has been done relatively recently. We will talk about this one later. But you can, yeah. So about the complexity of Nash, essentially, as I mentioned, the pure is easy. The mix is the one that I have mentioned in general. So let me see whether this is the case. So this is the one that I mentioned. This is like the one way that you can implement it. There are some better ways, essentially, that the people have considered it. But there is this result by this is the result, essentially, by I mean, Papadimitriou and Daskalakis, they could prove actually that for triple-layer game, finding the Nash equilibrium is p-pad complete. P-pad, essentially, what is the p-pad? Is the class that Christos introduced in 1994, and that's the one that shows that essentially defined is some kind of hardness. Like he introduced it in some senses. He mentioned to put the Nash equilibrium computation there, but it took maybe more than 20 years, essentially, or more to put this, to prove officially. But anyhow, so we know that, so he proved for triple-layer game, it is p-pad complete, and then there was another subsequent paper, essentially, by Shi-Chan, if I remember, that he proved essentially even two-layer games also p-pad complete. What's the meaning of that? This algorithm that I meant is exponential. It seems this is the best thing that we can hope for. We have it so far. Condition on the case that, and it is what's the meaning of p-pad complete. It means that if you can solve this problem, this class, we will talk more about. It has several other problems about fixed point computations, which are also hard. He proved that essentially this for the Nash proves that if you get some algorithm better than this exponential for Nash, you can also, because it is complete, you get solve lots of other problems, which so far believe that it is hard. But we don't have a proof, like we don't have p not equal to NP. The same thing here. We don't know that, but there's some evidence that at least this class of problem, Nash and set of fixed point computation problems, all of them are hard. So that's essentially the currency, but there are some heuristic, of course. The people have used some heuristic. For example, this is for the, if you want to consider two Nash, I mean, this is the basic thing that I mentioned. The people have tried to do it better for both two-player games and n-player games. These are some of the references. You can find more on that and the state of the art. But this was the idea that why Nash equilibrium, at least how can we compute it? What is the idea behind it? The proof of Nash also, you can take a look at it, but essentially uses the same idea that why always exists. Good. So I think we are done here for